Okay, so what this table is showing you is I just wanted to, this table is from your lecture book, and it just has some of the substances that are most commonly filtered out during glomerular filtration, okay? And don't worry about what milliequivalents per liter, it's the unit that these molecules they're measured in. Don't worry too much about what the unit specifically means. We're just going to pay attention to these numbers, and this would be the amount found in the plasma, the blood plasma. This would be the amount found in the glomerular filtrate, and then this is the amount that's actually found in the urine. And so there's some discrepancies with the numbers across the board. So, for example, sodium, if we look at sodium, 142 in the blood plasma, 142 in the glomerular filtrate, and then only 128 in the urine. So that means that some of this had to have gotten reabsorbed. And so remember those two other steps to urine formation. We have tubular reabsorption and then tubular secretion. Tubular reabsorption is primarily takes place in the proximal convoluted tubule, and that's because you have those simple cuboidal cells with microvilli, increased surface area, increased reabsorption. Tubular secretion can happen along the entire length of the renal tubule, but the bulk of tubular reabsorption takes place in the proximal. So remember, the kidneys, they're going to dump whatever can get out, whatever can fit through those fenestrae and slipwares will end up in the filtrate. And then the kidneys will say, oh, wait, no, I want to keep that. Oh, wait, I need to get rid of this faster than we can filter it out. So if the kidneys decide, nope, wait, we need to actually keep that, the body needs that right now, they'll reabsorb it. Or if we can't get enough of it out, that if we don't get enough out fast enough through just filtration alone, then we can have tubular secretion, which just is actively secreting more of whatever substance into the filtrate to be excreted as urine. And so sodium gets tubular reabsorbed. Now, a lot of these are going to be dependent upon what your body is like at that time, whether your body wants to reabsorb or secrete more. Bicarbonate, sulfate, phosphate, these are going to be important in especially bicarbonate will be important in maintaining pH balance. Let's see, glucose, 100 in the plasma, 100 in the filtrate, 0 in the urine. So there are active transporters in the proximal convoluted the cells of the proximal convoluted tubule that are responsible for actively reabsorbing, actively transporting all the glucose that's in the filtrate back. So we do not urinate our glucose out because glucose is a primary energy substrate, and so we don't get rid of it. We keep it and store it as glycogen, like in the liver or the skeletal muscle. So no glucose should be in our urine at all, and that's one of the the tell signs of diabetes is glucose in your urine, and that's because someone with diabetes, they overwhelm those active transporters in those cells. So there's so much glucose that's getting out into the filtrate that because your body either isn't making insulin or isn't recognizing your insulin. So there's so much glucose in the filtrate that those active transporters just can't work fast enough to reabsorb all that glucose. Urea is a metabolic breakdown product of proteins, and you can see 26 plasma, 26 filtrate, 1,820 in the urine. So this had to have been this would have been secreted. So some gets filtered out, but then even more is going to get secreted from those paratubular or vasorecta capillaries back or into the lumen of the tubule to be excreted. Uric acid is a breakdown product of nucleic acids. This also gets secreted. You can see 4, 4, 53. Creatinine, this is a muscle this is a metabolic breakdown product of muscle, and this happens at a steady rate throughout the day. And you can see 1, and then 196 in the urine. So that also had to have been secreted. So from the paratubular or vasorecta capillaries, that blood into the renal tubule to end up as urine, to end up being secreted in the urine. So this is just showing you the difference between our, this would be a normal systemic capillary. This is the capillaries in sequence in the kidneys. And so the kidneys, this is actually a portal system. And we've already talked about one portal system, and that was the hepatic portal system. And a portal system is where you go from capillaries through venules through another capillary bed. So you have two capillary beds in sequence. When we talked about the hepatic portal system, that blood was coming from the capillaries of the digestive tract through veins into the sinusoids of the liver, which is a specialized capillary bed. So this is showing you in our systemic capillaries, filtration predominates at the arterial end because of blood pressure, and then reabsorption of water and certain other substances would happen primarily at the venular end. This is showing you here that our capillary bed, this glomerulus, is highly specialized for filtration. And then as that blood moves from the glomerular capillaries into the paratubular capillaries or the vasa recta, anything that we want to keep that's in this filtrate, we will reabsorb it back into the blood. So that's tubular reabsorption. So glucose would be coming this way. Amino acids would be coming this way. Any albumin, which is a small plasma protein, any of that may have gotten out, it would be reabsorbed, right? And then anything from the blood plasma that we want to get rid of faster than what filtration can take care of on its own, we will secrete it from this blood in the paratubular or vasa recta capillaries and secrete it into the tubular fluid, that filtrate, to be excreted as urine. This is just showing you a few of, so this is, showing you things that we'll talk a little bit more about this next class, but it's just showing you things that are actively transported, passively transported, if it's being reabsorbed or secreted along the length of the renal tubule, what's happening in the loop of Henle. But main things I want to point out is like glucose and amino acids. These are things that will always get reabsorbed. And let's see, things that get secreted, like drugs or certain toxins and poisons that will get secreted so that it can be eliminated as urine. Okay, so now I'm going to talk about the juxtaglomerular apparatus. And so when you look, so here's our renal corpuscle, and this proximal convoluted tubule, which is much longer than the distal convoluted tubule, but highly, highly coiled. This is our proximal. And the way that you know which one's proximal is if it's directly connected to the renal corpuscle before this loop of Henle. This is all proximal, okay? And then here, this is the distal, okay? All right, so this is the renal corpuscle, proximal convoluted tubule, descending loop of Henle, ascending loop of Henle, and then you can see that this ascending loop, some books say it's the ascending, others say it's the distal convoluted tubule. It's right where the ascending is about to become the distal convoluted tubule again. It actually sandwiches up against the afferent arteriole of its own nephron, and that's what it's showing you here in higher magnification. So these cells that are right up against the afferent arteriole, and they're a little bit more columnar in shape, these are the macula densa cells. And if you tell me this is the ascending loop of Henle or the distal convoluted tubule, I'll accept either one. But these are the macula densa cells. And then you remember me talking about those enlarged smooth muscle cells that are right up against the macula densa cells. Those are the juxtaglomerular cells. The juxtaglomerular cells are specialized cells, and they have baroreceptors in them, so they are able to pick up on pressure changes. And so they monitor the blood pressure coming in right before it gets into this glomerulus. And so if they sense chronically low blood pressure, these juxtaglomerular cells are capable of secreting renin. Now, these macula densa cells, they pick up on concentrations of solutes in the tubular fluid. And so if they sense things like sodium and like certain ions are real low, that could mean that filtration is not happening here, right? Which could mean low blood pressure, right? Because what's driving filtration is a pressure gradient. And so these macula densa cells can signal low concentrations of solutes to the juxtaglomerular cells, and they in turn secrete renin. So renin enters into the blood. So renin from the kidneys would enter into the blood, and this angiotensinogen, which O-gin it should signal to you that it's inactive, is a plasma protein synthesized by the liver that's found in the blood at all times, but it doesn't get converted into angiotensin 1 unless renin is present in the blood plasma. And so renin gets secreted by those juxtaglomerular cells when there's chronically low blood pressure and or low concentrations of solutes that's picked up by the macula densa. And so when renin is present, it cleaves angiotensinogen into angiotensin 1, which is still an inactive form, until angiotensin 1 continues to circulate in the blood and it goes through the pulmonary capillaries in the lungs. And there's an enzyme found in the endothelial cells of the lungs called angiotensin converting enzyme, so ACE for short, ACE. And ACE will cleave angiotensin 1 into angiotensin 2, and angiotensin 2 is the active form, and it causes vasoconstriction, which increases blood pressure. Increased aldosterone from the adrenal cortex. This goes to the kidneys and specifically the distal convoluted tubule, and it increases tubular reabsorption of sodium. And when you reabsorb a sodium, a water follows with it passively, and so that helps increase blood volume, which would increase blood pressure. Increase ADH secretion from the pituitary gland. Antidiuretic hormone goes down to the collecting ducts. It increases the number of aquaporins, and so you increase water reabsorption, thereby increasing blood volume, increasing blood pressure, and also increase thirst, helping increase blood volume, increase blood pressure, because pressure, you have to have that pressure present to drive glomerular filtration.